Good afternoon, good morning, good evening, wherever you are in the world. We'll give it just 1 minute and then we'll get started. For everyone who is able to make it to the last event, I hope you enjoyed the conversation with some of the TAs and instructors about their career and academic journeys into quantum computing. If you missed it, the recording will be posted on Canvas later today. Okay, we can get jump in and get started. So hi everyone, I hope you've had a great week since the last time we saw you the same time last week. The really only big announcement from me, other than the regular make sure you're submitting your homework and attending your lab sections, is that the time many people have been waiting for is quickly approaching. We will soon start working with the IBM Quantum Experience, both playing around with circuits and then soon coding with Qiskit. So a few really exciting weeks coming up, but I want to, everyone will need to create an account with IBM Quantum Experience. That will be required for absolutely everyone, whether or not you're coding locally using Jupyter notebooks on your computer or you're working through the cloud. So I want Amir, who is an expert in IBM Quantum Experience, to share his screen really quickly and just show you how you'll create that account. And then later today and throughout this week, we'll be sending reminders and information through Canvas to make sure you have everything you need to create an account. It's really fairly simple, but we want to make sure it's straightforward and easy for all of you. So Amir, would you mind showing us how students will do that?
My pleasure, Rachel. So I'm going to stop sharing my iPad screen and switch over to my computer screen. Okay, let's.
And just so everyone knows, so you will need an account with IBM Quantum Experience, not for this week, but for your lab section starting next week. So you've got some time to do this, but it's better if you can start getting set up in case there are any bugs that we need to deal with.
Right, and it's super easy to actually set up the account. So first you need to go to quantum-computing.ibm.com. You could Google IBM Quantum Experience and it'll also direct you to this website. And you will see a page that looks like this. And to the right, there is an option that says new to IBM Quantum Experience, create an IBM ID account. So you just simply click on that. Now, of course, in my case, it's going to try to sign me up with my pre-existing IBM account, but let's just assume that I don't have an IBM account. So I click create an IBM ID, and then I see a page that looks like this. So here you enter the email address that you want to use for your IBM ID account. So let's just say I use my MIT email. And I already have an account with that, so I can't create another one, but first name, oops. Yeah, it's already telling me that this email exists. So maybe, okay, let's ignore this part. First name is Amir, last name is Karamlu in my case. Pick some password, and then you put which country you live in or you're residing currently. So yeah, and then you press next and you have to verify your email. You'll get sent an email to the email address that you put here, and then you use the verification code to verify your account. And it's just as simple as that. It basically takes 1 to 2 steps to make an IBM Quantum Experience account. And I believe, and again, Rachel, you can correct me if I'm wrong, this is all you'll need for your lab section in the coming weeks. And anything from there on, we'll walk you through it as well.
Yep, exactly. We will start to layer on levels of complexity. So eventually you'll be uploading Jupyter notebooks to the Quantum Experience or working with it locally for Qiskit. But for now, that's all you need to do. So please take the time in the next few days to create that account. And like I said, we'll follow up with written instructions too. But with that, those are my only announcements, Amir, if you want to take us off into the block sphere.
Okay, amazing. So yeah, let's talk about quantum computing then. In today's lecture, we'll mainly focus on the block sphere, and the block sphere is a tool to conceptualize the state of a qubit. So far when we've talked about qubits, of course, they've been somewhat abstract and unintuitive, but the block sphere is a mathematical tool to make the quantum state of a qubit a little bit more intuitive for us. And as an extension of creating a visualization for the quantum state of a qubit, we will use this tool to view how quantum gates act on our qubit state. It's a very powerful tool, very useful, and it could simplify some of the math a lot once you get comfortable with it. So again, with that, let's maybe talk about what a qubit is. We've mentioned a qubit many times throughout the course. But just to reiterate, a qubit is the building block of a quantum computer, and it is a two-level system. So if you remember, from the discussion that we had on spins and two-level systems are quantum systems that can be in a superposition of two possible values. So in the case of our quantum spin for the CERN-Gerlach experiment, those values were spin pointing up and spin pointing down. In the case of a qubit, these two values are 0 and 1. So again, similar to the idea of a bit that we're used to, quantum bits are made out of zeros and ones. But now what is special, of course, is all the quantum properties that come with having a quantum system. And you can put these qubit states in superposition of both 0 and 1 at the same time. So again, let's do another quick review. So the concept of superposition, tells us that a qubit can be in the state 0, and state 1 at the same time. And the way that we show the state of a qubit, and this is what you guys have seen throughout the past semester and all the lectures that we've had on quantum mechanics, is that we show it as psi is equal to the alpha times the 0 state plus beta times the 1 state. And of course, something that we've discussed is we use the matrix mechanics version of quantum mechanics, in which we can represent any quantum state as a vector and any quantum operation as a matrix. So in this case, if you want the vector associated with the 0 state, it's just this column vector with 1 as a top entry and 0 as the bottom entry. And the 1 state will be a column vector again with 0 as a top entry and 1 as a bottom entry. So basically, using this, we can also, again, this is all review. We can write the arbitrary state psi that we have as a vector as well. So again, we said that psi is alpha times the 0 state, and what we discussed is that the 0 state is 1, 0 plus beta times the 1 state. And the 1 state can be represented with the vector 0, 1. And of course, this will give me alpha on top, 0 on the bottom, plus 0 on top, beta on the bottom. And I can just simply add these like you add any vectors, and you end up with alpha on the top, beta on the bottom. And again, as a point of review, again, we will see this in a few slides again. This alpha and beta are both complex numbers. So this just means complex. And magnitude alpha squared plus magnitude beta squared has to add up to 1. And again, that comes from the fact that the probability of getting a 0 when measuring this quantum state is alpha squared, magnitude alpha squared rather, and probability of measuring the 1 is magnitude beta squared. And these probabilities, when you add them, since you have two possible outcomes, need to add up to 1. Okay, with that, let's do a quick review of complex numbers, because again, as I mentioned, alpha and beta are complex numbers. So complex number, or rather a complex number, consists of both a real and an imaginary component. So in this case, let's take z to be a complex number. Oops. Okay. So z's are complex number. Here, a is the real part, and I times b is the imaginary part. So basically, whatever number is multiplied by the I, that becomes the imaginary part of our complex number. Now, of course, we can have a complex conjugate of a complex number, and maybe I'll write this here. And we show this with the star. So Z star means complex conjugate of Z. And the only thing that happens when you take the complex conjugate of a number is that you flip the sign in front of the imaginary part. So up there rather, we had Z is equal to A plus IB. Now the complex conjugate of Z would be A minus IB. And something that's nice, that's convenient about these complex numbers, of course, is that you can show them on a coordinate system similar to the Cartesian coordinate system that we're pretty comfortable with by now. So over here, the x-axis would be the real part of our complex number, and then the y-axis would be the imaginary part. So based on that, if I tell you that I have, a z value that, would be that point, the point that I just highlighted on this coordinate system, what is the value of z? Maybe think about it for 10 seconds and then we'll go through it together. So in this example, z is equal to what? And again, this is something that we've seen in the past, so I just want to quickly review it. So, okay, so the value of z on the real axis is 3. So I have z is equal to 3 plus, and then the value of z on the imaginary axis is 2. So I get an I2, or maybe I can write that as 2i also, but let's say I times 2. So that is the value of z. Again, z is a complex number, and I'm showing it on a coordinate system. Now, something that I'm telling you, and we're going to explore this more in the next slide, is that the amplitude squared of z is the same as either multiplying z by the complex conjugate of z, or vice versa, multiplying the complex conjugate by z. And maybe let's quickly do that with the example that we have over there. So I told you that z is a plus ib, and again, a and b are arbitrary numbers. So z times complex conjugate of z would be a plus ib times a minus ib. Okay, so far so good. And again, this multiplication is similar to the binomial multiplication that you guys have seen before in your high school courses. So I'm going to have, okay, a times a gives me a squared. Then I have a here times minus ib. That gives me minus I times ab. Again, I here is the imaginary number, of course. And here I have, okay, so now I'll move on to the next part of the first parenthesis. So I have ib times a. That gives me plus I ab. And then I'm going to have plus ib times minus ib. So that is minus I squared times b squared, right? Okay, so let's go through this one step at a time. So here, this minus IAB and plus IAB will cancel each other out. So I'm going to end up with a squared. And now, if you guys remember, the definition of I was square root of 1. And again, as a reminder. So I squared would just be minus 1. And I have a minus sign there, so what I end up with is a squared plus b squared. And from a geometric picture, this should make sense, right? Because again, if we look at it on this coordinate system, if we call, this distance A and this distance B, then the magnitude, the length of z squared will be a squared plus b squared. That's just a Pythagorean theorem. And that is where this assertion comes from, essentially. Okay, with that, let's explore these complex numbers a little bit more. So again, something that we discussed in the first lecture was Euler's formula, which states that if I have e to the I phi over here, I can write that as that is equal to cosine phi plus I sine phi. Now, I'm not going to sketch the proof for you, but you can explore it more if you're interested. The proof comes from using something called the Taylor expansion, which is a very useful tool in mathematics in general. Okay, so in other words, I can show this EI phi again as a point on a, well, in this case, a unit sphere, because the amplitude of EI phi is 1, where the projection onto the real axis, or the amount that we go on the real axis, is going to be cosine of phi, and the amount that we're going to go on the imaginary axis is sine of phi. And of course, the angle that we're making with the real axis is phi. So that's the point. And why am I talking about the Euler formula? So let's discuss that a little bit more. It's a very convenient way to represent, using this polar representation. It's a convenient way to represent the complex numbers, not as x plus iy, but as some magnitude times something called a phase, which again we'll talk about more. So in this case, what I'm claiming is that if I have a complex number that is x, that is equal to x plus iy, I can write that as this amplitude of z. And again, as a reminder, amplitude of z is just the square root of x squared plus y squared. Again, that comes from the Pythagorean theorem, right? Like the amplitude is just the length of this line over here. And the phi here, of course, is the phi that we see in this picture. It's the angle that we make with the real axis. So I have cosine phi plus I sine phi. And again, this is very suggestive, right? So this part, if you guys remember, we can use the Euler identity or Euler's formula to write as EI phi. So what we're doing in a polar representation is that instead of writing our complex number as x plus iy, we're writing it as some magnitude or amplitude, say magnitude here, times some phase. And again, I can derive the values for r and phi, both using what the values of x and y are. And yeah, this is a review of what we've seen during the first semester. Fan talked in detail about Euler's formula and the complex exponential. Now, a part that I want to discuss a little bit more today is what is phase. So I said that this EI phi component, that's a phase. And again, as a reminder, from Euler's formula, we have EI phi. That, like, you can either write your phi's like this or like this. They're the same. So that is equal to cosine of phi, in this case, plus I sine of phi. And this is a very slight entity. We're going to say it over and over again. Now, okay, maybe let's take a minute and figure out what is the amplitude of E phi I. So like e to the power of I phi, what is the amplitude or the magnitude of that? So yeah, take 30 seconds to a minute, and using this definition and what we've defined as the amplitude in the previous slides, I mean, either one of these two really, tell me what is the amplitude of this EI phi. Okay, maybe we can start discussing this together now. So what we saw from the previous section is that this amplitude is simply square root of x squared, the imaginary part, the real part, plus the imaginary part squared. So square root of real part squared plus imaginary part squared. Okay, so in this case, let me draw the square root. My real part is cosine of phi. So let's say cosine squared of phi. And the imaginary part is just sine of phi. Again, the I is the thing, the number that indicates that, that is the imaginary part. So I have cosine squared of phi plus sine squared of phi. And of course, from trig, we know that cosine squared of phi plus sine squared of phi is equal to 1, and the square root of 1 is just 1. So again, the thing that's special about this phase is that the magnitude of the phase is equal to 1. So we can always demonstrate this on a unit sphere. And again, the phase is something that we're going to see when we talk about the block sphere, but I just want to do a quick review so we're comfortable with what the phase is. And of course, we can try what the value is for different values of phi. So let's say I have this ei phi. What if phi is equal to 0? Then what do I get? Well, then ei phi is equal to e to the power of 0, and anything to the power of 0. Actually, or maybe let me just expand this. So I have cosine of 0 plus I sine of 0, right? And cosine of 0 is 1. Sine of 0 is 0, so we get 1 here. Now, if phi here is equal to, let's say, pi over 2, then I'm going to have e to the I times pi over 2. And of course, I'm going to use the Euler identity to expand this now and write it as cosine of pi divided by 2 plus I sine of pi divided by 2. Okay, cosine of pi divided by 2. And again, as a reminder, pi divided by 2 in radians is equal to 90 degrees. Cosine of 90 degrees is 0. Sine of 90 degrees, or pi over 2, is 1. So what I end up with is I. And maybe let's do one more example. So let's say, what if phi is equal to pi, or 180 degrees? So e to the I pi would be equal to cosine of pi plus I sine of pi. And again, here pi radians is 180 degrees. Cosine of pi, or again cosine of 180, is -1, and then the sine of pi is just 0. So the real conclusion is that this phase, again, based on what the value of phi is, can have any of these values. And if you check them, like 1, like 1 squared, the amplitude of 1 is 1. Of course, the amplitude of I is also 1, and then the amplitude of -1 is also 1. So it matches with what I told you earlier about the fact that if we look at the phase, the magnitude of phase is always 1. Okay, let's move on to the next slide. So now what I'm going to tell you is that in quantum mechanics, the global phase has no physical significance and no effect, and therefore can be ignored. So what do I mean by global phase? If I have a state psi and I write a phase ei phi in front of it, I can just ignore this phase and just write my state as psi. Again, the reason for that is going back to the postulates of quantum mechanics that we talked about in the previous lecture. We care about, when we talk about the theory of quantum mechanics, we care about properties that we can measure. However, this phase in front of here cannot be measured using, if there's a global phase in front of psi. There's no way that we can measure that phase, therefore we can ignore it. So for example, let me maybe write this as an example. If I have, -0, I can just write this as 0, right? Because again, this minus is a -1, and it's a global phase, so I can ignore it. Now, so I told you guys that global phases can be ignored, but there's of course a subtlety. So if I have, let's say, 0 minus 1, and let's do divided by square root of 2 to get the normalization correct. This is not the same as 0 plus 1 divided by square root of 2. So now this minus sign here between 0 and 1 is not a global phase, but rather a relative phase between 0 and 1. And that is actually something that we are able to measure using quantum mechanics and in lab. And again, this is something that we're going to see again in the context of the block sphere, but I just wanted to point this out so this doesn't cause confusion. Okay, so let's talk about the block sphere now. You might have seen this schematic multiple times throughout the course, because the state of a qubit can be represented as a point on the block sphere. So this block sphere is a unit sphere, which means that the radius is always equal to 1. So yeah, the radius of the sphere is always equal to 1. That's just what unit sphere means. And what I'm telling you is that, if I have a quantum state of a single qubit, a single 2-level system, I can represent this as a point on this block sphere, on a unit sphere. Okay, so let's see why I'm making that claim. And let's start with, again, our definition of qubit, which was, which was alpha 0 plus beta 1. Okay, so again, what we talked about is alpha and beta are complex numbers, right? Or are just complex if I'm writing it in plain English. So what this means is that I can write alpha, let's say, as magnitude of alpha times some phase, which I'm going to call EI, and let's say phi of alpha. Okay, and beta I can also represent the same way. I can write it as magnitude of beta times EI phi beta. Okay, so let's do that. Okay, so based on this, psi is going to be equal to magnitude of alpha times EI phi alpha. So magnitude times phase of the first complex number, of course, in front of the 0 state, plus same deal, magnitude times phase in front of the 1 state. So the magnitude is just beta in this magnitude sign, and then the phase is EI phi beta times the 1 state, of course. Okay, what I'm going to do next is that I'm going to factor out the phase in front of the 0 state. So what I'm going to do is that I'm going to write EI phi alpha here, right? I'm pulling it out, and then I'll do a parentheses, magnitude of alpha times the 0 state plus magnitude of beta. Now, what we have here is, so I factored out an EI phi A. So what I'm going to have here is an I phi beta minus phi alpha. Of course, and this is in front of the 1 state. Okay, so far so good. So now I have a question, and I realize that there's no poll. I haven't set up a poll ahead of time, so there's no way for me to get feedback. But my question is, and I want you to think about this maybe for 10 seconds, and is that, can I ignore this phase? Or actually, maybe I will recycle an old poll, but unable to access canvas is not a valid answer here. So yes or no, can I ignore that phase? Okay, let's give it 10 more seconds. But I like what I'm seeing as with the poll results so far. Okay, so the majority have said that yes, we can ignore this phase, and in fact, that is true. So the wave that I've written this part of our phase is just a global phase. And again, as I mentioned on the previous slide, global phase can be ignored. Okay, now I'm going to relaunch the poll. What about this phase? Is this something that I can ignore? And again, unable to access canvas is not a valid answer. Okay, let's take 20 more seconds and try to answer this question. Okay, yeah, and again, the overwhelming majority, have a good idea of what's happening. So now this phase is a relative phase between the 0 and the 1 state. So it can't be ignored. It actually is physically meaningful. Okay, so for that, I'm just going to write, I'm just going to say that phi, this new variable phi, is equal to phi beta minus phi alpha, And that's just to simplify things. Okay, so what we discussed is now I can write my quantum state as, again, magnitude alpha times 0 plus magnitude beta times ei phi times the 1 state, in front of the 1 state. Okay, now for the next step, I would like to go back to another property of this alpha and beta that we talked about, and that is that alpha squared plus beta squared is equal to 1. Now, what does this remind you guys of? And maybe I'll try to make this again a little bit suggestive by going back a few slides and maybe looking at what we have here. So cosine and sine might be a good candidate, right? Oops, I definitely went too ahead. Okay, so if I say that magnitude alpha is equal to cosine of some other parameter theta over 2, and magnitude of beta is sine of theta over 2, then magnitude alpha squared times or plus magnitude beta squared gives me cosine squared of theta divided by 2 plus sine squared of theta divided by 2. And that is equal to 1. So I can go ahead and replace this alpha and beta with cosine and sine, which ends up being, okay, so my quantum state psi, I end up being able to represent this as cosine of theta divided by 2 times 0 plus sine of theta divided by 2 times the 1 state. So we went from, oh, and of course, let's not forget about the phase, before we get too excited, ei phi, of course. So we went from representing the state of the qubit as alpha times the 0 state plus beta times the 1 state as cosine of some parameter theta divided by 2 plus sine theta divided by 2 times the phase times the 1. Now, why is this useful? Well, turns out that I can actually use this definition to show the state of my qubit on a unit sphere. Again, why is it a unit sphere? Because if you remember, the overlap of psi with psi needs to be equal to 1 for any quantum state. And therefore, the magnitude of the overall thing, the radius of the sphere will be 1. And now this angle theta, oops, this angle theta that we have here will just be the angle that our point makes with the z-axis, and phi is going to be the phase angle phi here that we have is going to be the angle that our point makes with the x-axis. So in this definition of a Bloch sphere, the North Pole is the 0 state, the South Pole is the 1 state, and a classical bit, in contrast to a quantum bit or a qubit, can only be strictly on the North Pole over here or on the South Pole over here, and nowhere in between. Whereas a quantum bit, a quantum state, can be anywhere on the surface of this sphere. And this is the best way to draw a distinction between, again, classical computing, a classical bit, and a quantum bit. Again, just to recap. So based on this Bloch sphere definition that we defined, a classical bit can only be at 2 points, either North Pole or the South Pole, whereas a quantum bit can be anywhere on the surface of the sphere. Or rather, the state of the quantum bit can be anywhere on the surface of the sphere. Again, no, just to reiterate, we can show the state of our quantum state as cosine theta divided by 2 times 0 plus sine theta divided by 2 times I phi times the 1 in front of the 1 state. And this theta and phi are I think this is called the polar angle and the azimuthal angle of the point on a sphere. Okay, so what if theta is equal to 0? What quantum state do I get? So let's look at this definition, then we're going to look at a picture on the Bloch sphere. So maybe think about this for 30 seconds, and we'll go through it together. And actually, I'm going to launch a poll. So let me know, what your thoughts are after you think about it for a little bit longer. Okay, I'm going to end the poll in a couple of seconds. And again, a good number of you gave the correct answer. So if theta is equal to 0, my psi is going to be equal to cosine of 0 divided by 2 is 0 times the 0 state plus sine of 0 e to the I phi. And again, I didn't define a phi, but now the idea is that, okay, sine of 0 is 0, so this thing is entirely 0, and cosine of 0 is 1. So what I end up with at the end of the day is the 0 state. And now let's look at this on the Bloch sphere. So if this angle theta is equal to 0, then my state psi is at the North Pole, correct? It's over here. And the North Pole of the Bloch sphere is a 0 state. So everything should make sense, hopefully. Now, okay, the animation is a little off. So now what if theta is equal to pi? And again, I will relaunch the poll. Think about this for 30 seconds, and then we'll do this together. And again, I would like to encourage you to think about this in two different ways. Like, right, first of all, by just looking at the definition that we gave, the mathematical definition, and also try to think about it in terms of, like how would it look like on the block sphere? This geometric visualization that we have for the qubit. Okay, let's try to get some more answers in. I'm going to end the poll now. And again, most of you gave the correct answer. So let's again do this first of all using the bracket notation that we have, and then we'll discuss it using the visual block sphere tool that we have at our disposal. So here I have cosine of, so theta is pi, so pi over 2, which again is 90 degrees, times 0 plus sine of pi over 2, ei phi, and I didn't define a phi, times the one state. Okay, so cosine of pi over 2 is 0. Sine of pi over 2 is 1. So what I'm going to end up with is I phi times 1. And I would like to launch another poll, and that is, can I ignore this I phi? So can I ignore this phase? Yeah, and again, the overwhelming majority of the answers that I'm getting is that yes, because again, remember, this is a global phase now. There's no, there's no zero component to this superposition anymore. So whatever phase is in front of 1 is just global phase, and I can ignore it. So I just end up with the 1 state. Okay, now let's think about this, again, as the picture on the block sphere. So if this angle theta is equal to pi, or 180 degrees, my state psi is going to be exactly on the south pole. And the south pole of the block sphere is the 1 state. So again, the whole point of this exercise was to give you an idea of how you can use this visual representation combined with the tools that we have from matrix mechanics and the Dirac notation to figure out exactly what the quantum state of what a quantum state is based on different parameters. Now let's look at again something a little bit more exciting. So what if I say I'm looking at theta is equal to pi over 2 with a phi of 0. What state do I get then? And again, try to do this by yourself for 30 seconds, let's say, and I'm going to launch a poll now, and let me know what you got. So what quantum state do I get for this value of theta and this value of phi? Okay, let's take another 15 seconds to just let me know what you got. Okay, so let's start doing this together now. So what I said is that, okay, theta is equal to pi over 2. So I'm going to have the quantum state psi is going to be equal to cosine of pi divided by 4, since theta is pi divided by 2, and we have it divided by 2 there, times the 0 state plus sine of pi divided by 4. And pi divided by 4 is 45 degrees, for those of you who are more comfortable with degrees. And here, of course, I said that phi is equal to 0. So I have e to the I times 0 in front of the 1 state. Okay, so e to the I 0, e to the 0 is just 1, so we can ignore that. Now, cosine of pi divided by 4 is 1 divided by square root of 2. So I have 1 divided by square root of 2, 0. And sine of pi divided by 4, or 45 degrees, is also 1 divided by square root of 2. So what I end up with is 0 plus 1 divided by square root of 2. And that, actually, most of you got that correct, by the way. And if you want to think about this again as a picture on the Bloch sphere, so the angle theta pi over 2 corresponds to us being on the equator, and when phi is equal to 0, we're along the x-axis on the equator of the Bloch sphere. So, exactly between 0 and 1. And also, I mean, that is kind of an indication that if we try to measure the state along 0 and 1, or you make a computational basis measurement, we're going to get 0 with 1/2 probability and 1 with 1/2 probability, because we're exactly in between. We're on the equator. And okay, let's see. I can go, okay, yeah, a little off with the animation. And another example that I want you guys to think about is, what if theta is pi divided by 2, but phi is equal to pi now in this case? And again, let's take 30 seconds to think about it. I'm going to relaunch the poll, so let me know what you get. Okay, let's take 15 more seconds now to get in our answers if we have them, and then we can go through this together. Yes, I'm going to end polling now. And again, an overwhelming majority of you also got this correct. So I have psi here, and again, theta is pi over 2, so I'm going to have cosine of pi divided by 4 times the 0 state plus sine of pi divided by 4 times e to the I pi now, because this azimuthal angle phi is equal to pi times the 1 state. So something that we discussed in the previous slides was that e to the I pi is just equal to -1. And what I end up with because of that is 1 divided by square root of 2, which is the value of cosine of pi divided by 4 times the 0 state. Now minus 1 divided by square root of 2 times the 1 state. And of course, this gives me, I can just rewrite as 0 minus 1 divided by square root of 2. And if we think about this in terms of where the point would be on the Bloch sphere, it's going to be on the equator again, but in the exact opposite point than like the direction that the x-axis is pointing. And also, this should now make intuitive sense, with the conversation that we had about measuring in different bases. So what I told you is that when we measure along, let's say, well, the z basis, which is our computational basis, we get 0 or 1. And we see that those are the points on the block sphere along this z line. So 0 is in the positive direction, and 1 is the exact opposite in the negative direction. Now this 0 plus 1 divided by square root of 2, and this 0 minus 1 divided by square root of 2, which again were the, if I want to write a review, the plus state that we talked about and the minus state that we talked about, were the possible outcomes of measuring along the x direction. And again, what we're seeing is that these 2 points are in the positive direction and the negative direction of the block sphere along the x-axis. So this is another way that the discussion that we had about measuring along different axes ties back to this representation that we have in terms of the block sphere. Again, the block sphere is a very powerful tool because of that. So with that, let's take a 10-minute break, and then we're going to come back and talk about quantum gates. And we'll, of course, answer some questions right after the break. So yeah, now it's 2:53 Eastern Standard Time. So let's take a break till 3:03 Eastern Standard Time. Okay, it's 3:03 everyone, so let's get started. But before we dive into the content of the second half of the lecture, maybe let's answer a few questions.
Cool, let's do it. Amir, can you help us remind us the difference between magnitude and amplitude?
Yeah, so they're the same thing. You can call it either the magnitude of your complex number or the amplitude of your complex number. And again, I mentioned earlier in the lecture, you can't go back and forth with that. And I do that sometimes, and people do that. So just the TLDR is that magnitude is the same thing as amplitude.
Cool. Thanks for that clarification. A few questions about global phase. So you talked about this at the beginning, but remind us because it's really important. Why can we ignore the global phase and why can't we measure it?
Yeah, so well, I guess what I mentioned is that the reason why we can ignore global phase is because it's nothing that we can measure. And I can also expand that claim to say that it also doesn't affect any of our quantum operations past that point. So once you have a global phase, essentially like every operation that you apply to your quantum state, that global phase will just stick around. By the time you get to measurement, regardless of what you're trying to measure, if you're actually, let me try to use this feature. If you have I phi psi, and you try to find the overlaps, let's have like some state psi prime is equal to that. Then the overlap of psi prime with psi prime is going to be equal to psi e psi phi times e I phi times psi. And of course, these two will cancel each other out. So you end up with psi. And regardless, if you're trying to like measure the expected value for an operator, let's say, like you're trying to measure psi prime x psi prime. Again, this is what we talked about from the postulates when we mean like measure something along the x-axis, for example. Like this is a measurement along the x-axis, now instead of the z-axis that I talked about earlier. In this case, the same thing holds, right? I have psi ei minus phi, this operator x, maybe I'll put the hat on top so we know it's an operator, ei phi psi, and again, these two will cancel each other out. So what you end up with is psi x psi. So this is what we mean when we say you can't measure it. Like if you have a global phase in front of your psi, if you try to measure anything, it's as if you're just measuring the state psi at the end of the day. So that's why I say you can ignore this. But also if you're applying operators, right? So if you're like, let's say, you want to apply an X operator, or let's call it sigma X, same thing. Sigma X to psi prime, again, this ei phi will just stick around and your X will be applied to psi. Because this is a constant, right? So you can move it around. It's not like an operator which the order matters. So at the end of the day, again, once you get to the measurement phase, when you're actually trying to link your quantum state to the classical world, this e to the I phi, this global phase will be still sticking around. And again, you can't measure it, so you can ignore it. And that's what I mean when I say there's no physical significance.
Okay, so for anyone who might have gotten a little bit confused or lost in the details, can you just give us like the most simple definition of phase? The message you should take away.
I mean, I can go back a few slides because we have the definition here. So this part, this is phase. It's e to the I phi such that the magnitude of this is equal to 1. Like, yeah, anything like this, anything in this format is a phase.
Perfect. And Akshay, I think you wanted to jump in with an analogy for global versus local phase.
Yeah, so I like to think of phase in terms of running around a track. So imagine that you're running around a circular track, like in like one of those Olympic tracks that you see. So the phase is basically the angle that you make with like the center of the track, kind of like what Amir was just describing. And so now imagine that you're running with your friend. So you're like running, both of you are running along the track, right? And you're interested in finding out where your friend is relative to you. So that would be like the relative phase. It would be basically the difference between like the angle that you make and the angle that your friend makes. And global phase would be basically like asking, how many laps have you done in total, right? So for that, you would have to like go all the way around the circle as many times as as many laps as you've taken. And in quantum mechanics, that's not a very, it's, as Amir was saying, it's not something that makes a difference to any measurement that we make, how many laps you've taken around. The only thing that matters is where you are with respect to your friend, the relative phase between the two of you. Another point that someone brought up in the chat was that, I think it's a really good point, is that phase is only meaningful when it is relative to something. Without having like some reference to measure the phase with, phase does not really mean anything. It's the same thing as asking the question, how many laps have you taken, is only meaningful if you have a starting point. Otherwise, you can't really measure how many laps you've taken. And so that's why we can ignore global phases, because there is no reference for it. And for relative phase, there is always a reference. And so it is something that is measurable and makes a difference.
Yeah, that's a great point, actually. That's a great way to visualize it. And again, to emphasize, it's not only that we can't measure global phase, but it doesn't influence any future operations. So now you can apply as many quantum operations, as many quantum gates as you want to your quantum state. And the fact that the global state is there or not doesn't matter. So literally from its conception to when you measure it, it doesn't matter. So we ignore it in quantum mechanics.
Cool. Two more questions.
Any other questions? Amazing.
Yeah. Why can we equate alpha to cosine theta over 2?
Well, okay, so I think we can agree that it's not wrong to say alpha is cosine of theta over 2, right? Because at the end of the, or rather magnitude or amplitude, same thing, of alpha is equal to cosine of theta over 2. Because at the end of the day, cosine squared plus sine squared gives you a 1. Now, the reason why there's a theta over 2 there instead of a theta goes back to math. So by representing the block sphere the way that I did to you, I'm kind of shoving a little bit, well, actually not a little bit of math, but plenty of advanced math under the rug. And that's something that doesn't get covered in normal physics course. So you oftentimes have to go to like further advanced math in order to actually understand the reasoning behind that. But if I were to give you an intuitive picture, the reason for that is because we're going from a world where everything can be complex to a world that's real, to a 3D world with all real components. So we're going from essentially a 2D world with all complex variables to a 3D world with all real. And through that mapping, something that happens is that, some parts of our first world, some part of our first world will be associated, the 2D world with complex numbers will be associated with 2 points on the second world, which is a 3D world with all real numbers. And that is a property of math. And the theta, the divided by 2 essentially comes to be able to resolve that in a way. And I know any mathematician will not be happy with what I just told you guys, but that is just an intuitive picture. Of course, again, there's more rigorous reasoning behind this, and for those of you who are interested, I would highly encourage you to go and look at it. maybe look at SU2 to SO3. So SU2 is that 2D world but complex that I was talking about, and SO3 is the 3D world but real. So 2D complex, 3D real. And again, don't worry about it. This is something that I personally did not understand until I had to teach it, and I realized people are going to ask me this question, so I really had to look into it. But to get started and to do quantum computing, or to use the block sphere for that matter, you do not need to know what SU2 means or SO3 means. But if you're interested, go look it up.
I still don't understand any of this, and when I see it written down, I take it as my cue to leave the conversation. So bye, everyone.
Don't
Yeah,
leave
and,
up.
and Akshay has a PhD. So again, you don't need to know what this is. Akshay has a PhD. He deals with quantum mechanics every day, and he still doesn't know what these are, like what the rigorous math definitions are. So it's totally fine.
Yeah.
But the answer to your question is, again, the TLDR is that the reason why there's a factor of 2 over theta over 2 instead of theta is because of some mathematical mapping.
Cool. I mean, maybe to Akshay's point, as a reminder for everyone, if you don't understand every detail of any of these lectures, that's okay. The goal is exposure and getting you comfortable with the foundation. So I hope folks don't feel like they have to get caught up in the details. And as always, there are lots of resources like Piazza and Friday office hours in case you are feeling confused. One final question, Amir, before you get back into it. Connecting concepts we've talked before about, so entanglement with the block sphere. When we have 2 entangled qubits, can you represent them both on the block sphere? Or how would you?
Yeah, so the block sphere is meant to represent the state of a single qubit. And it actually is a little bit, it has like many shortcomings when it comes to describing systems of more than a single qubit. For example, it can't capture correlation between qubits like entanglement. So yeah, there's no good way of capturing entanglement in its entirety using block sphere. But it's a really good way of, again, visualizing the state of a qubit, or multiple qubits for that matter. It's just like when it comes to correlations between qubits, it's not baked into it. And actually, to Rachel's point, before I dive back into the lecture, a lot of the times, again, as someone who does quantum computing and who's teaching it right now, like I don't know everything about quantum computing, everything there is about quantum computing, and that's just how the cutting edge science works. Like, there's no way there's let's just say there's no way that you can understand everything, all the subtle details about quantum computing or quantum engineering and things like that. There are parts of the problems that are more interesting to theorists, parts that are more interesting to experimentalists, parts of the problems that are more interesting to mathematicians, for that matter. So if there are things that you don't know, that's totally fine. Again, I would be the first person to tell you, and I mean, Akshay just said, there are so many things, even about quantum computing, that I don't know, and I've been doing this for 7 years now almost. And I mean, I've been teaching it for 4 years. And that's totally fine. I can still do my research. I'm still contributing to quantum computing, all these things. And I mean, I'm still a scientist, hopefully. But again, if you don't know what SU2 or SO3 means, chances are you might not need to know what it means. So don't get bogged down if if there are details that you're missing. But again, I would encourage you to go and explore these more if you find them interesting, because that's the best way to get started in the field, to find like areas that you're interested in and kind of focus on those. Okay, with that out of the way, let's get started with the second part of our lecture. So in the first part of our lecture, we talked about quantum states and how we can represent the state of a qubit as a point on the surface of something called the block sphere. But now let's go back to quantum gates, which we talked about. So again, as a reminder, quantum gates map one quantum state to another quantum state. Or in other words, you can think of them as moving your point on, you moving your point from point A on the block sphere to point B on the block sphere. Now, of course, something that we've discussed in the past and we're going to see in the next slides is that we can represent them with matrices. Now, an analogy that Rachel and I came up with is, a travel analogy. Let's say, you're somewhere on the surface of Earth, in some country or some state. Let's say, you're in Cambridge, Massachusetts, and you want to go to Cambridge, UK. You get on a plane and you fly to, well, you probably have to fly to London because I don't think you can fly to Cambridge, UK directly. But let's say you fly into Cambridge, UK, and you can think of a quantum gate as something like taking a flight from one point on your Bloch sphere, in this case, on Earth, to another point on the Bloch sphere or Earth. So that's a good visual to have in mind in terms of what quantum gates do. Yeah, some important quantum gates that we've discussed so far, of course, are the Pauli gates or the Pauli matrices. That's sigma x here, which is 0, 1, 1, 0. We call that the Pauli X operator. And sometimes, a lot of the times, we go back between showing it as sigma x or as just an x, like what we have here. Another operator is a sigma y operator. Again, it looks like 0 minus I 0, and then we show it as y. And another one, another important one is the Pauli z operator, which is just 1, 0, 0 minus 1. And again, sometimes we just show it with a single z. So we've seen these before. We've seen them in action a little bit. And again, we've talked about how we can associate measuring a qubit along different axes, let's say, to these Pauli operators. But now we're going to take it a little bit further by, of course, like thinking about these operations along the Bloch sphere. So let's start with the Pauli X operator. What happens when I apply the Pauli X operator to the 0 state? So Pauli X applied to 0. What do I get? And let me start a poll maybe for this. So what does Pauli X apply to 0? And again, of course, as practice, maybe on this first one, we can write this as a vector matrix multiplication. So the matrix for Pauli X is 0, 1, 1, 0. And the vector for the 0 state is just 1, 0. Okay, I'm going to end the poll again. The result's very clear. But let's just do this together. So when I do this matrix multiplication or vector by matrix multiplication, I get 0, 1, which is the 1 state. So the Pauli X operator applied to the 0 state gives me the 1 state. And the Pauli X operator applied to the 1 state gives me, again, I'm going to repeat this again, but maybe I'll stop at some point. 0, 1, and this gives me the 1, 0 state, which is, of course, if I show it as using the bracket notation, it's just a 0 state. So what we've discussed before is that you can think of this as a quantum bit flip, essentially, in the computational basis, of course. Now, let's see what happens on the Bloch sphere. Oh, amazing, the animation's working. Perfect. So the Pauli X operator rotates our quantum state around the x-axis by 180 degrees, or pi radians. And again, this animation, I think, does a good job of demonstrating that, how we go from 0 to 1 with, we rotate by pi radians, or 180 degrees. Okay, next let's consider the Pauli Z operator. So what happens when I apply sigma Z to the 0 state? And maybe I will launch the poll so we can answer this. Again, for practice, let's just write this in terms of vectors multiplied by matrices. Okay, and polling again. Yeah, most of you got it right. So yeah, when I do this matrix multiplication, I just get 1, 0. which is the 0 state. Now, what if I apply the sigma z to the 1 state? What do I get then? Actually, this is a good question to relaunch the poll on. Okay, I'm going to end the poll. I think we have a majority. So of course here what we're going to get is 0 minus 1, which I can show as minus 1 state. Now, if you look at this immediately, you might be like, okay, this negative 1 that I have in front of my 1 state is just a global phase, so can be ignored, and that's true. But if you have any superposition of 0 and 1, of course, then that phase will become a relative phase. So let's just keep it there for now. And what this Pauli-Z operator really does, again, in a computational basis, is that it's a phase flip operator, or let's just call it a phase operator. Again, there are no classical analogies because in the classical world, there's 0 or 1, and phase doesn't mean anything. And what it really is a rotation around the z-axis by 180 degrees. Now, if I'm on the north pole of the block sphere and I rotate by 180 degrees around the z-axis, what do I get? Where do I end up? Well, I'm not gonna move actually. I'm always gonna stay on the north pole. So that's why when I apply the sigma z operator to 0, I see nothing moving. Alternatively, if I'm on the south pole at the 1 state, if I apply the sigma z operator, if I rotate by 180 degrees around the z-axis, I'm still going to stay at the 1 state. I mean, and that is similar to what we're seeing when we apply the sigma z operator to the 1 state. We see that we end up at -1. And again, remember, in that case, negative is a global phase that you can ignore. So we never really move from the 1 state when we're on the south pole and applying this 180 degree rotation. Of course, we'll see maximal effect of the z operator when we're on the block sphere equator. And that's actually what I have here. So if we start from the plus state, which again, if you remember, plus state is 0 plus 1 divided by square root of 2, and the minus state is 0 minus 1 divided by square root of 2. Then when we apply a z operator to the plus, we see that we get the minus state. And again, that's because that when we're on the equator, we're maximally sensitive to the changes to the relative phase between 0 and 1. Okay, maybe let's move on to the next slide now. And of course, another Pauli operator that we discussed is the sigma y operator, as is displayed above here. So now let's try applying sigma y to the 0 state. What do I get? And I think the options aren't actually captured in the poll, so unfortunately I can't relaunch the same poll, but let's just do this again together. So I have the operator times the 0 state, and what I end up with is going to be 0 times 0 on top and I on the bottom. And that I can rewrite as I times 0. And if I apply this Pauli y operator to the 1 state, I get 0, I mean, same matrix multiplication essentially. But now what I end up with is negative I on top and then a 0 on the bottom. So I end up with, oh, and actually this should be a 1, by the way, that was a mistake. So I end up with negative I times the 0 state. And looking at this now, to me, it seems like this Pauli y is a combination of our bit flip and our phase flip. In other words, if I were to just, put an I here, let's say, so if I'm applying this Pauli y, and I'm now going to show that's y to the 0, that seems to be the same as if I had an I here, and x, a y, an x, a z, applied to the 0 state. And in fact, this is true. So, something that, you guys will see over and over again is that sigma y, and again, I'm going between showing the Pauli y operator as y and sigma y deliberately because they're interchangeable. So sigma y is equal to I sigma x sigma z. That is a property that's true. So really, you don't need the Pauli y operator. You can just construct it using sigma z and sigma x.
Amir, could I jump in with a question I'm getting in the
chat? Yeah, go for it.
So here we have an I in front of the 1 and a minus I in front of the 0. Mm-hmm. So are those global phases? And if so, could we ignore them?
So in this case, yes, they are. And again, this is similar to the negative that we got when we're doing when we're applying the z state to 0 and 1. Now, where things become interesting is when you apply this y operator to not 0 or 1, but a superposition. Because then, of course, this phase will matter. And that's why I haven't dropped the phase, because again, while in this case it is a global phase, if we apply this to any superposition, it becomes a relative phase all of a sudden, and it makes a big difference. And actually, we can see the action of the Pauli y operator here. Again, it is a rotation around the y-axis by 180 degrees. So if we start from the 0 state, we're going to end up at the 1 state. And again, to Akshay's point in the question in the chat, then this I, if we start from the 0 state and end up in the 1 state, the I will be a global phase and can be ignored. But in general, I think the takeaway message is that all these Pauli operators, x, y, and z, are rotations by 180 degrees around their respective axes. And that's why they get the name x, y, and z. Now, so what we've talked about so far is rotations by 180 degrees or pi radians on the Bloch sphere, but we're not limited by just 180 degrees. We can rotate by really any angle that our heart desires. So in this case, what I'm showing is, and again, we're going to discuss this in further detail in next slides, but just a notation. I'm showing a rotation, which I show with R, around the x-axis by pi divided by 2 radians or 90 degrees. And that's how I show it. Now, I can rotate by any arbitrary angle theta around any axis that I want, x, y, or z. So here, a rotation around the x-axis by an angle theta can be shown as this unitary operation. So e to the I theta divided by 2 sigma x. Now, I say that this is unitary, and the reason for that is because sigma x, sigma y, and sigma z are all Hermitian, if you remember. So that basically makes it such that this exponential is unitary. And again, a key point here, of course, is this theta over 2. So when I'm rotating by an angle theta, the exponent that I have will have it divided by 2 in it. So yeah, and of course the biggest difference here is based on which axis I'm rotating around, I'm going to get different Pauli operators here. So when I'm rotating around the x-axis, I get a Pauli x in the exponential. When I'm rotating around the y-axis, I get a Pauli y in the exponential. When I'm rotating around the z-axis, I get a Pauli z in the exponential. So two key takeaway points. First of all, the axis of rotation determines what Pauli operation goes in the exponential. And then the second one is that in the exponential, whatever this angle is, we divide it by 2. And of course, there's a negative I theta divided by 2 times sigma x. And this negative is just convention. Okay, let's make this a little bit more concrete. So let's look at the Pauli X operator, or rather rotating around the x-axis by angle theta. So what I just told you is that I can represent it using this exponent. And now something else that I will tell you without proving it here is that I can represent this e to the negative I theta divided by 2 sigma x as as this combination of a cosine and sine theta over 2. And again, this comes from a Taylor expansion. We're not going to go into detail on that in this lecture, but if you're curious, you look it up. So I can show a rotation around the x-axis by theta radians as cosine of theta divided by 2 times I, where I is the identity operator, time minus here. Now this I is the imaginary number, sine theta divided by 2 times, in this case, the Pauli X operator. Now, what will this look like? What is a matrix representation? Okay, let's do this together. So I have Rx of theta, and what I said is that that's equal to cosine of theta divided by 2 times the identity matrix. And again, if you remember, the identity matrix is just 1, 0, 0, 1, minus I, here, this I is the imaginary number, sine of theta divided by 2 times the sigma x operator. And the sigma x operator is 0, 1, 1, 0. So if I expand this, actually, maybe let me do this in 2 steps. So I'm just going to multiply this scalar that I have with my matrix. So the first part is going to be cosine of theta divided by 2 on the diagonals, and nothing on the off diagonal elements. And here I'm just going to have minus I sine theta divided by 2 times the matrix elements, and that will give me a minus I sine theta divided by 2 on the off diagonals, basically. And still 0 on the diagonals. And actually this will be a plus because I already absorbed the minus inside the matrix. Okay, and I can just add every single element by every single element in this matrix. So what I'm going to end up with is cosine theta divided by 2 minus sine of theta divided by 2 minus sine theta divided by 2 and cosine of theta divided by 2. And really the takeaway message from this slide, from what I just did, is that you can show all these rotations on the Bloch sphere around some axis by some arbitrary angle, as with a matrix. Again, these are valid quantum gates because they're unitary operations. And what we've talked about is all quantum operations, at least in the world that we're talking about, in the world of quantum computing, can be represented as a matrix. So in this case, we showed it for a rotation around the x-axis by angle theta. Now, for practice, let's try to find the matrix representation for a rotation around the z-axis by some angle theta. And again, the expansion works exactly the same, except for that now, since we're rotating around the z-axis, we're going to replace all of our Pauli operators with Pauli z. So maybe let's take a minute or two and try to do this by ourselves. Work out what the matrix representation is for a rotation around the z-axis by some angle theta. Okay, let's try doing this together now. So what I just said is that RZ of theta is equal to cosine of theta divided by 2 times the identity operator, which is 1, 0, 0, 1, minus I sine of theta divided by 2 times the Pauli-Z operator, which is 1, 0, 0, negative 1. So what I end up with here is that for the first element, I'm going to have cosine of theta divided by 2 minus I sine theta divided by 2. Now the 0, 1 element, the off-diagonal element, will just be 0. And the other off-diagonal elements is also going to be 0 because, again, all these off-diagonal elements here are 0. And my 1, 1 matrix element, or the bottom right matrix element, is going to be cosine of theta divided by 2 plus I sine of theta divided by 2. So this is a matrix representation for a rotation around the z-axis by an angle theta. And you could also repeat the same process for rotation around the y-axis by angle theta. I'm not going to go through it in lecture today, but I would encourage you to attempt that. Okay, with that, let's look at a few examples. So let's say I start from the state 0 and I rotate around the x-axis. Again, we saw an example of this, of course, by pi radians. So I apply an Rx pi to the 0 state. What do I get? And maybe I will launch the poll for this. Okay, I think the majority of you have it correct. So maybe before I, write out the math, let's think about the intuitive picture and the visual picture that we've learned using the block sphere. So if I'm starting from the 0 state up top here, rotating around the x-axis by pi radians will put me exactly at the 1 state. I'll go from the North Pole to the South Pole if I rotate around the x-axis by 180 degrees or pi radians. So what I expect to get is the 1 state. Now let's try doing it, using the tools that we have. So okay, what I said is that I can show Rx of pi as cosine of theta divided by 2 times the identity minus, in this case, I sine of theta divided by 2 times sigma x. And this is applied to the 0 state. Now, this would be the same as if I were to apply each operator separately to the 0 state. So maybe let's do that first. So I have cosine of theta divided by 2 times I acting on 0 minus I sine of theta divided by 2 sigma x acting on the 0 state. Now, cosine of theta divided by 2, or cosine of 90 degrees, is 0. So what I end up with is, and sine of pi over 2, or sine of 90 degrees, is 1. So what I end up with is minus I sigma x times the 0 state, and the sigma x will flip the 0 to a 1. So I end up with a minus I times 0, and times 1. And of course, what we've talked about is here, this is a global phase, so we can just ignore it. So an Rx rotation by pi radians will give me the one state. And sometimes actually this is referred to, like, if we're talking about the experimental world, sometimes we refer to this as a pi pulse, meaning that it applies a pi degree rotation either on the x-axis or sometimes the y-axis. Okay, now let's look at another example. What if I apply an ix, but rotate by pi over 2 instead of pi to the 0 state? What do I get then? And maybe I will relaunch the poll so you can let me know, what do you get, but think about this for 30 seconds first before you submit an answer. And maybe I will, help you guys out a little bit by expanding this. And I understand that this question might be a little bit trickier than you think. So don't worry if you get a little bit surprised. Okay, I'm gonna end polling now and we can go through this together. So let's first do this using the bracket notation and the bracket representation, then we can talk about it on the block sphere. So here again, what I'll tell you is that each one of these operations can act on the 0 state separately. So I can write this as cosine of pi over 4 times I acting on 0 minus I sine of pi over 4 times sigma x acting on, again, 0. So cosine of pi divided by 4 is 1 divided by square root of 2, and then the identity doesn't do anything to the 0 state. So what I end up here with from the first part is 1 divided by square root of 2 times 0. And now the second part, I'm acting with sigma x on the 0 state. That gives me a 1. So I'll have I, and sine of theta over 4 is 1 divided by square root of 2, of course. Sine of pi divided by 4, sorry, 1. And of course, if I were to write this out, it would be 0 minus I times the 1 state divided by square root of 2. So actually, most of the answers that we got this time around were wrong because this phase in the middle is different. And intuitively, if you think about it, when you're rotating around the z-axis, the x-axis by pi over 2 degrees or by 90 degrees, you actually end up along, on the y-axis, not the x-axis, right? Because again, you're rotating around something. You're rotating around this x, so you end up along the y-axis. And turns out that one of the eigenvalue, the eigenstate of the y operator they end up at is this one. So not 0 plus 1 divided by square root of 2, but rather 0 minus I times the 1 state divided by square root of 2. If you still measure this, you're going to get 50% 0, 50% 1. But it's not exactly the plus state, but rather it's the eigenstate of the y, say Pauli y sigma, a Pauli y operator, because you end up along the y-axis. Okay, let's keep the examples going. So now what if I apply a rotation around the y-axis, again, let's say by pi over 2 to the 0 state? What do I get then? And maybe I'll relaunch the poll. And And while you guys are thinking about it, I'll just again expand this rotation around the y-axis by pi over 2 based on the like the cosine and sine components that we've seen. So this is if I had cosine of pi over 4 times the identity minus I sine of theta divided by 2 times sigma y. And this is applied to the 0 state, of course. Okay, let's end the poll and go through this together. So same deal as last time, we're going to approach it the same way. So I'm going to apply each part of this operator separately. So I'm going to have cosine of pi divided by 4 times I acting on the 0 state minus, again, the imaginary number sine of, and sorry, this theta divided by 2, of course, should be pi. So let's do pi divided by 2. Pi divided by, this should be pi divided by 4. I don't know what happened here. Sigma y acting on 0. So the identity acting on 0 doesn't do anything, and the cosine of pi over 4 is 1 divided by square root of 2. So from the first part, I get 1 divided by square root of 2 times 0. And okay, this second part. So sigma y acting on the 0 state gives me I times the 1 state. So maybe let me do this. So I get I times the 1 state. And here I'm going to have I times minus I, which gives me plus 1. And then the square root sine of pi divided by 4 is just 1 divided by square root of 2. Oops. And okay, well, the example got erased somehow. So let's just quickly do this again. So that's, yeah, I'm just going to continue from where I left off. So that's cosine of pi divided by 4 times the identity acting on 0 plus, or sorry, minus in this case, I sine of pi divided by 4 sigma y acting on the 0 state. And what I get from the first part is 1 divided by square root of 2 times the 0 state, because the identity acting on 0 doesn't do anything. And then sigma y acting on 0 gives me I, the imaginary number, times 1. And that I, when I multiply by this I, gives me minus 1. So I end up with plus 1 divided by square root of 2, 1, which is the plus state that we're used to. So 0 plus 1 divided by square root of 2, or, also the plus state. And also, again, when we look at this on the block square, visually, this should make sense, because when I'm rotating around the y-axis now by pi divided by 2 radians, or 90 degrees, I end up on the x-axis. And again, the point that I end up at is the plus state. Okay, let's do one more quick exercise before we move on. So let's say now I have my my plus state, and I apply a rotation around the z-axis now by let's say pi over 2. Because pi is a full sigma z operator, so let's do pi over 2 around the z-axis to the plus state. What do I get in this case? Well, so before we do anything with the math, let's look at it on the block sphere. So the plus state is here, right? So this is the plus state. And now I'm rotating by pi over 2 radians around the z-axis. So I'm rotating around here. So I will end up from being along the x-axis to going to where the y-axis is. So I'll end up here. So I'm running on the surface of the sphere, of course. And if we remember from the previous, from what we had on the previous slide, this was 0 minus I1 divided by square root of 2. So that's what I expect to get if I work out the math here by myself. So let's do that maybe. So again, I'm going to repeat the same process. And of course, as we're getting more comfortable with different tricks when it comes to Pauli X, Pauli Y, Pauli Z's applied to 0, 1s or plus minus states, we can utilize some more. So this is the first part. This is the cosine of theta divided by 2. In this case, theta is pi divided by 2. So I have pi divided by 4 times the identity acting on 0 minus I. And sorry, this is not the 0 state. Of course, this is the plus state. Minus I sine of pi divided by 4 sigma z, in this case, acting on the plus state again. So what do I end up with? So I have, in this case, cosine of pi divided by 4 times I, the identity acting on the plus state doesn't change anything. So I get 1 divided by square root of 2 times the plus state. Now here, sigma z acting on the plus state will give me the minus state. This is what we saw a few slides earlier. So I can write this as minus I divided by square root of 2 times the minus state. Okay, so far so good. What next? Well, okay, to actually get something in terms of the plus and the 0 and the 1 state from the plus and the minus state, let's expand. So I am going to factor out a 1 divided by square root of 2. And actually, I'm going to factor out 2 of these. So one from what I have over here and another one from when I talk about the plus and the minus state. So I'm going to end up with 0 plus 1. And again, I've already factored out that 1 divided by square root of 2. That goes from going from the plus state to 0 and 1 state. And now this is going to be minus I times the 0 state plus I times the 1 state. And of course, if you do some math, which I'm going to avoid doing here, you'll see that by factoring out some overall global phase, you can write this as 0 minus I1 divided by square root of 2. Again, I'm skipping the math here just for the sake of time and also because we don't get anything out of it intuitively. But really, this goes to show how powerful of a tool the block sphere is when it comes to thinking about single qubit rotations and things like that. Because here, of course, we start from the 0 state. We know exactly where we end up. We end up at a familiar state, and then we can apply a z rotation. And again, we know where we're going to end up on the block sphere. And since we've actually calculated what that state is earlier, we can expect that after applying the sigma z operator without doing any math, we're going to end up at that state. Okay, so let's talk about what are the experimental implementations of these rotation operators that I talked about. So all the quantum gates that we implement in a quantum computer are engineered using rotations on the block sphere. And in fact, in our quantum hardware or quantum computer, we can control each of these rotations and transitions to to some decent level of accuracy. So what I'm showing you here is a Rabi oscillation that I took in lab a few days ago. And what I'm doing here essentially is that I am applying a rotation about the x-axis with some angle. So in this case, of course, the angle is determined by the amplitude that I have here. And what happens is that I go from 0 all the way to 1, and at different points throughout this transition, I actually measure the quantum state of the system, or measure the state of the qubit along the z-axis. So before I do anything to the qubit, I expect to be close to, let me zoom in here, close to 0. And that's what happens. So the average state of my qubit is in the 0 state. And of course, as I keep on applying this rotation to the qubit, I get closer and closer to the 1 state. So I reach the 1 state somewhere around here. So this is where the state is 1. This is where the state is 0. And what you see here is the average population again as I go from 0 to 1 along different points. So in fact, what I'm doing is that I'm we call this driving the qubit. I'm driving the qubit between 0 and 1, and I'm just choosing different points along this transition, along this drive, or along this rotation, and I just measure the qubit population. So what is the probability of being 0? What is the probability of being a 1? And I can see that I gradually get closer from 0 to 1. And of course, if I keep this going, this rotation going, I'm going to go back from 1 to 0. And that is something that you start seeing here. It's like the population of the qubit starts going from mostly being in the 1 state to getting closer to being in the 0 state. And we can just basically go around, loop around the block sphere this way many times. Okay, in the interest of time, I'm going to quickly go through quantum universality, and again, this is something we'll see later on in the course, hopefully. But the concept of universality actually comes from classical computing, and that is that if you have a set of gates, we can do any quantum computing operation using these set of gates. So now for quantum computing, in order to be able to do any quantum computing operations, we need a combination of these 4 gates. So the C-knot we've seen, and we're going to discuss this in more detail in future lectures, that is a controlled knot between two qubits. So this is a 2-qubit gate. The H is the Hadamard, and then the SNT I'm going to talk about on the next slide. So the S gate is just a rotation around the Z gate, around the Z axis by pi over 2 degrees. And you can show this actually as 1, 0, 0, or I think it's I. Yeah, because, yeah. Or in other words, and this is what I was thinking, S squared is equal to Z. So that's all the S gate is, and that's actually something you'll see in the quantum experience. Now, the T gate is just a rotation around the Z axis by pi over 4 degrees. And what, the form of it is just going to be 1, 0, 0 minus I pi divided by 4. Actually, I think there might be a minus here. And now the important thing here is t to the power of 2 is equal to an S gate. And because of that, t to the power of 4 is equal to a Z gate. So again, all these extra 2 gates that we just talked about are in rotations around the Z axis. One by pi divided by 2, and another one, so this is S, and another one, which is a T, is by pi divided by 4. And that's about it. So given these rotations that we talked about, plus the Hadamard gate, plus some 2-qubit gate, which we'll visit in the future lectures, we're able to do any quantum computing operation possible. And again, that's why we talked about that. That's why we focused this lecture on the block sphere and quantum gates, especially framed as rotations on the block sphere. Because it actually turns out that we can use this as a tool to do any quantum computing operation, run any quantum algorithm that we want. So with that, I would like to wrap up this lecture. Not sure if there are any questions, but no, I'd be happy to answer a few if there are any pressing ones.
There was a quick question about the direction of rotations. So when we apply the rotation gates on the block sphere, are the rotations clockwise or counterclockwise?
The rotations are always counterclockwise. And actually, that brings me to a good point that I didn't mention, but again, as we mentioned, these rotations are unitary operations, those are quantum gates. So, if you are rotating, let's say, counterclockwise by pi over 2 radians, you can cancel it out by rotating counterclockwise or in the opposite direction by pi over 2 radians. Okay, if there are no other questions, thank you guys. Sorry we went a little bit over time, and I hope you have a great week.